Okay, in this video, I'm going to focus on some relative motion problems that are a little bit easier to solve by just remembering what the concept of relative motion is in the first place and doing a simple diagram and getting straight to the answer. Here we have a ship traveling in the water, and the water is going to be moving, and we want to know the boat's actual velocity relative to the Earth. So the ship is moving at 5 meters per second north, and the water is flowing at 3 meters per second east. So the ship tries to go up like this relative to the water. That's the velocity of the boat relative to the water. And then that the current is going to push it a little bit east of where it thought it was going to go. 3 meters per second east. Now, yeah, you could recognize that these are already components, and essentially what we are doing is using the component method. But if we remember, this is the velocity of the water relative to the Earth. Or if you will, this is the current. So, it is components, and we are just really recombining our components at this point. But if we just think about it as the boat tried to go up here and got pushed over this way, then we can see that the actual velocity of the boat relative to the Earth is here. VBW plus VWE is equal to VBE. Boat relative to the Earth is equal to the boat to the water plus the water to the Earth. And instead of worrying about components and all that kind of stuff, we can see we already have a right angle triangle here, and we can just solve for this hypotenuse directly. So h squared is equal to a squared plus b squared. So we can get a hypotenuse here of 5.83. Remember here that all of these are velocities, which means they're all vectors, so we also need the direction. Always put the direction where you started. And here, that makes this the opposite and this the adjacent. So tan theta, which is opposite over adjacent, is 3 meters per second over 5 meters per second. And that works out to 31 degrees. So, boat tried to go up, got pushed over a little bit, and ended up going 5.83 meters per second north, 31 degrees east. Essentially, all we did here was exploit the fact that these were already in our north and east directions separately, so we can just recombine them a little simpler. Okay, here's another one. A swimmer wants to swim directly north across a river, so they want to go straight north. The river is 30 meters wide. The swimmer can swim with a maximum speed of 2.0 meters per second relative to the water, and the current is flowing at 1.0 meters per second east. So if it's 1.0 meters per second east, and it calls it the current, that we know that the current really means the velocity of the water relative to the Earth. That's our current. And we know that the velocity of the swimmer relative to the water has a magnitude of 2.0 meters per second. That says the fastest they can go, but we don't know the heading. What heading should the swimmer use to get straight across the river? How long will this take? How long would it take them to swim across if they just let the current push them downstream? So, again, conceptually, you can think about this. If you want to get going straight across, you're going to need to swim upstream a little bit and let the current push you downstream. If you can swim at 2.0 meters per second and the current's going to push you back at 1.0 meters per second. This is the velocity of the swimmer relative to the water. This is the velocity of the water relative to the earth. Then we can see here we have the velocity of the swimmer relative to the earth. To get the heading, I simply have to look at this angle, although I'm going to need this value so that I can figure out how long this will take. Let's start with the heading. Careful here, we almost always seem to be using tan when we're looking for angles, but we got a different triangle than we're used to seeing here. This is the opposite of the triangle, and this is the adjacent of the triangle. Or not the adjacent, sorry, that would have given you the 10. That's the hypotenuse of the triangle. So here we have the ratio of opposite over hypotenuse, and that's actually the sine of theta. And this turns out to be one of our special triangles, so I don't have to use my calculator here. Theta is just equal to 30 degrees. But if you use your calculator, it'll give you 30 degrees, so it's fine. So the heading you want to use is north, and then 30 degrees towards the west. That way, when the current pushes you east, it'll push you back in line with the north. Now, for this value, we can get it a couple different ways. We can use trig, or we can use the Pythagorean theorem. I find trig a tiny bit easier, so let's use trig. This is the adjacent side. So cos theta is equal to my adjacent over my hypotenuse. So that's the cos of 30, which is equal to VSE over my hypotenuse of 2. Cos 30 is one of those special ones, 0.866. 2.0 meters per second. If you haven't done functions and you don't know what the special triangles are, you can just use your calculator there, but if you know what they are, it's 0.866. So multiplying that by 2, I'm going to get 1.732 meters per second. Okay. So let's just again do a quick recap of this conceptually. You try and swim upstream, it pushes you back downstream, and we can see that this side is a little bit shorter. And so some of the lost speed, but it's all on different angles, so we got to use trig or the Pythagorean theorem to come up with 1.732 meters per second. Now, if you'll recall, the river was 30 meters wide, and we're dealing with we're going to assume anyways that this is a uniform velocity situation. So V is equal to delta D over T, because the acceleration is 0. So 1.732 meters per second is equal to your delta D. You have to go 30 meters across the river over T. Again, this is one of those situations with the variable on the bottom, so we multiply both sides by the variable. Assuming T isn't equal to 0, if T equals 0, then that'll screw this up, but it's not, so it's okay. We'll divide both sides by 1.732 meters per second. And that's going to give us 17.32 seconds. So it's going to take us about 17 seconds to get across this river. Okay. So we've got the heading. We've got how long the trip will take. Now the last question says, how long would it take if you just swam straight across and let the river push you downstream? What that means then is that you're going to direct yourself straight up and let the river push you downstream a little bit. What's going on in this problem is that the river itself is still only 30 meters wide. So you have to go, if you're going like this, you're going to go end up going like this, but this component of your velocity is the one that's getting you across the river. That's the 2.0. So I don't really care. It didn't ask how far downstream I'm going to land, although I guess I could figure that out. What I'm really interested in here is just with this component, how long is it going to take for me to traverse the 30? Delta D is 30. My v then this time going across the river is 2.0 meters per second. And we're going to assume you're just doing this at a constant, or that 2.0 represents an average velocity or whatever. So my acceleration is 0. So v equals delta d over t. 2.0 meters per second equals 30 meters divided by time. Again, multiply both sides by time. Get them to the top on the other side. Divide both sides by 2.0 meters per second. And t this time is 15 seconds. So this is interesting. If we try and correct ourselves so we get directly across the river, it's going to take 17.32 seconds. We lose some of our velocity to battling that current. On the other hand, if I try to go straight across, I'm going to get pushed downstream, but it's going to take me only 15 seconds. This is why they say that if you're in a river or something like that, you shouldn't try and swim against the current. You should just try and go perpendicular to the current, because it lets you cover more distance in less time. So there's a couple problems where it was easier to use the diagram than to solve in components. You can solve this problem in components. It actually becomes kind of difficult and a little bit confusing. So this is the best approach. And we try and learn things like components because they're consistent, good ways, but of course there's lots of ways to solve these problems. So that's it.